All right, students, we are coming back to our lecture, and this is the third hour of our lecture. So, we have talked about how to calculate the parameters of the the cellular systems. So, for example, the cell area and also circular uh, the cell radius of the circular cells and um, bandwidth, so on and so forth. Now we are going to do uh, a little bit of calculations for that. Okay, so next slide. So a particular cellular system has the following characteristics. Its cluster size is 7 and its uniform cell size. And user density is 100 users per square kilometer. An frequency spectrum allocated frequency spectrum is 900 to 949 megahertz. And then the bit rate required per user is 10 kbps. So as you may recall, 10 kbps is the conventional rate for voice communications for uplink and 10 kbps for downlink, and the modulation call rate is 1 bps per hertz. So if we are using FDMA FDD, then how much bandwidth is available per cell using FDD? So it's 49 megahertz over 7. How is this done? It comes from this 900 to 949. So as a result, 49 divided by 7 is equal to 7 megahertz per cell, because that much bandwidth is divided into 7 portions, and 7 portions is each portion is given to a cell. So that is 7 megahertz per cell. So for FDD, uh, frequency division duplex, that frequency division meaning that each direction for uplink and downlink is given half and half of the bandwidth. As a result, the 7 has to be divided by 2, because uh, one part for uplink, one part for downlink. So 3.5 for one direction, which is uplink or downlink. And then how many users per cell can be supported using FDMA? It's 10 kbps per user. As a result, 3.5 megahertz divided by 10 kHz per user, which equals 350 users per cell. Okay, so let's say you have 3.5 megahertz for uplink, but each user demands 10 kilohertz. As a result, you divide 3.5 by 10k, and that gives you 350 users per cell. Then what is the cell area? 100 users per square kilometer equals 3.5 square kilometer per cell. right? How is that done? That comes from um, we have uh, 350. 350 comes from available bandwidth and the demand for each user. That gives you 350. So we are trying to accommodate 350 users per cell. And then what is the cell area? Uh, we are trying to find an area that accommodates 350. Since we have 100 users per square kilometer, then 350 uh, divided by 100 is 3.5, and then we will say it will be 3.5 square kilometer per cell. Okay, and what is the cell radius assuming circular cell? The cell radius, pi r squared, this r represents the radius. A radius for a circular cell, and its area is pi r squared. Then it equals 3.5. As a result, we have r equal to, pi is 3.14, something like that, right? So we have 3.5 and r equal to 1 point. It's just solve for r, and you get r equal to 1.056 km. And then we come to question B. If the available spectrum is divided into 35 channels and TDMA is employed within each channel, then what is the bandwidth and data rate per channel? At 3.5 megahertz divided into 35, which is equal to 100 kHz per channel. As a result, it will equal to 100 kbps. 100 kbps. That's data rate per channel. And how many time slots are needed in a TDMA frame to support the required number of users? I want to bring to your attention just a little bit uh, for the TD and FD concepts. We go back the slides a little bit. Uh, Here we have T, time, and then frequency. So what we just calculate is available bandwidth divided by number of users. So we get this. Now we are calculating how the time slots should be separated into different sections, and each section is for a user. Virtually, we will think one session as a virtual channel. Why? Because we think we should think this way. The pattern is going to be repeated. For example, 1, 2, 3, 4. 1 is going to be repeated somewhere around here, and then repeated somewhere around here again, again. So virtually, we have a time slot associated with a specific user. So we call it a channel, and that channel can be used by a specific user. So with a little bit of review, now we come back to our calculation. Since we have a channel 100 kbps, then how many time slots are needed in a TDMA frame to support the required number of users? We have 10 kbps per user, that's a requirement, but we have 100 kbps per channel. So what that means is each channel can support up to 10 users. 10 multiplied by 10 is equal to 100. So we can support up to 10 users per channel. If the TDMA frame is 10 milliseconds, then how long is each user slot in the frame? If the TDMA frame is 10 milliseconds, so recall that what do we mean by 10 TDMA frame? A TDMA frame is a frame that has a whole set of the sessions and it repeats itself. So let's say 10 milliseconds, meaning that for a frame it has 10 milliseconds. But we are accommodating 10 users, right? 10 users in a frame which is 10 milliseconds. Then we will divide 10 by the number of users, which is what happens here. Which is what happens here. A frame is 10 milliseconds, and we have 10 users to jointly utilizing this 10 milliseconds. So for each user, it's given 1 millisecond because we divide 10 milliseconds by 10 and you get 1 millisecond. How many bits are transmitted in each time slot? We have 1 millisecond for one user, but the bit rate is 100 kbps. As a result, you multiply 1 millisecond by 1 kbps, you get 100 bit per slot. Remember that the k is equal to 10 to the 3. The ms meaning that mini means 10 to the minus 3. So 10 to the minus 3 and 10 to the 3. So we multiply this, you get 100b per slot. So now we have each slot given 100 bit for transmission. So that's how we calculate. Recall that if you are given the settings, then how do you calculate sort of the parameters, the bit rates for each user, the size of the cells, so on and so forth. You get things done and clarified. Okay, so that solves the problem. Now we go to the GSM, which is 2G TDMA. So now it goes to the introduction. The circuit mode data. Circuit means a connection. It means a connection through the wireless all the way up to the central office. Okay, so transparent mode, non-transparent mode using radio link protocol, and then the data rate up to 9.6 kbps. And also there is a short message service. Nowadays in 4G, 5G, we still have short message service. except that it's not used very often though. But you can still find that function in the cell phone. But it used to be a common practice when people are trying to send just a little bit of information. You use short message, but nowadays people use, the message applications, app, message app like Line, WhatsApp, and WeChat, or even Google Chat, Facebook Chat. There are a lot of chat services. They just go through data channel, but that short message is going through communication channel, and it's limited to 160 characters. And packing more data plans for uh, GSM Phase 2 Plus. And architecture specifications very detailed with a lot of white papers, and it defines several interfaces for multiple suppliers. Okay, so now this is the cellular architecture. You have a subscriber identity module that is embedded in your mobile equipment. So if we try to see it this way, your mobile station, the cell phone, so-called cell phone, or sometimes we use UE, user equipment, which includes this module. And then the base station subsystem, which includes the whole bunch of stuff. That is the base transceiver station, base transceiver station. You have multiple. When it repeats, it means you have multiple. Uh, so you have base transceiver station, and that connects to base station controller. Then it repeats itself. It has multiple stations, and it connects all the way up, and then it connects up to this network subsystem. That network system includes home location register, visitor location register, mobile service switching center, and equipment identity register, authentication center, and all those functional blocks is included in this network subsystem. And then when you see this, that means it's connected by wireless connection. And when you see this, it's connected physically by a wire. It's either uh, uh, it's fixed line, DEM 9 fixed line. So it connected by fixed line, but this is connected by wireless. And as you can see here, you have a register to register what cell phones identities are in this cell, with what cell phones are visitors. Visitors meaning that they come from other cells. Their home register is somewhere else. It does not belong to this cell. It's just a visitor. And so let's say you move from cell A to cell B, then cell B maybe your role will be a visitor in the cell B, and cell A may be your home register. Okay, so then there's a mobile service switching center, and you have identity register and authentication center, which authenticates by, by some protocols such that uh, your cell phone is identified as the authentic cell phone, instead of being uh, a fraud. Some people may get frauded, you know, if they will you, uh, some people steal your identity and try to fraud, and they can use your cell phone to make phone calls, and the bill will be billed to you. That's not fair. So uh, you try to authenticate that your cell phone is authentic. And then the mobile service switching center connects to the conventional PSTN, which is the landline. The landline. Okay, so that's three part mobile station, base station, network subsystem sort of consists of the whole cellular architecture. Okay, so each station has certain functionalities. So the mobile station and base station subsystem, the mobile station uh, communicates across user interface. Uh, that is the air interface wireless with base station transceiver in same cell as mobile unit. Mobile equipment uh, is the physical terminal such as telephone or PC. Some nowadays some you know pad or PC or laptop computers, they have a physical entity to let you put in the SIM card. When you put the SIM cards in, it becomes a mobile equipment. Okay, uh, as long as it runs the protocol and it serves the functionality of the cellular system. A mobile computer, a PC, or a, a laptop, they can serve as the mobile equipment. And that ME, the mobile equipment, includes radio transceiver, digital signal processor, and subscriber identity. So that's what I mean. There needs to be a SIM card. And GSM subscriber units are generic until SIM card is inserted. So the GSM subscriber units are generic until SIM card is inserted. The SIM's ROM necessarily the subscriber devices. Okay, the BSS, which is the BSS, base station subsystem. Base station subsystem consists of base station controller and one or more base transceiver stations. So you have a transceiver, you have multiple transceivers. So for example, this one is taking care of a couple of users. This one could be taking care of a couple of users. So BSC uh, uh, reserves radio frequency, manages handoff of mobile unit from one cell to another within BSS and controls paging. Then network subsystem center. Mobile switching center is a core. So that's sort of a core network and consists of several databases. So let's move back a little bit. This whole thing is in the center of the network and it consists of a couple of databases. Those databases going to register information for the UEs and then doing authentication and registration and then communicate with the LAN 9, the PSTN. So network switching center is a core, and it consists of several databases. Home location register database, which stores information about each subscriber that belongs to it. And visitor location register database maintains information about subscribers currently physically in the region. An authentication center database used for authentication activities and particularly encryption keys. So as we look by overview, we'll see you have a register to store information about subscriber, and register maintains information about subscriber, but those subscribers does not belong to that register. They are visitors physically in the region, but they are visitors. And then database AUC used for authentication activity, and it holds an encryption key, meaning that if a user claims to be someone claims to be a specific device, it will use encryption key to authenticate that user through some encryption decryption protocols and authenticate that uh, user is not fake. It's real. It's authentic. And equipment identity register database, it keeps track of the type of equipment that exists at the mobile station. So let's take a look at the service, how the service is done. This is in GSM, but not only in GSM, it actually applies to various protocols. It's like people do it similarly, except some terminology will be different, but most cellular systems, 4G, 5G even, do it similar ways. So you have a BTS. Of course, you have a cell phone first. You have a cell phone. Then you have BTS, base station, and it communicates with this MSC and gateway MSC, and they have their databases. And then if you are communicating with another cell phone, then what happens? You communicate with BTS. It goes to MSC, and the MSC communicating with another BTS, and that BTS is communicating with another cell phone. So it goes through things like that if you have another cell phone. But if you are communicating with a LAN 9, what happens is it goes through here, and then here, and it goes to gateway, goes to PSTN, and then goes to the phone. So this is sort of the way cell phone communicate with cell phone, or cell phone communicate with a fixed LAN 9. And if we try to look at the steps, this number represents the steps, and each step is described here. So let's take a look at this step by step. The first thing is this phone initiates a call, and it goes to its PSTN, And that PSTN identifies that the receiver is a cell phone, so it will make a request to this gateway. And this gateway will check with its database and see if that cell phone is in its home or in its visitor. If it's in its home, then it goes back. Otherwise, it checks with the visitor location register. And then the visitor location register tells that yes, that cell phone is under our control, but it's a visitor. Then it gets the information back to this home register, and this home register will tell the gateway saying that yes, the cell phone is under our control, but it's a visitor. Then then the gateway confirms that the cell phone is under control of this base station, and then it tells the sends the information to this MSC, and that MSC then checks again with a visitor database, and then it gets the, the database gets the information back to MSC, and then the MSC communicates with BTS, and then BTS will initiate a wireless communication with the cell phone. That is when wireless is initiated. And then when the wireless is initiated, the information will go back. There's a loop, downlink, uplink, downlink, uplink. There will be a communication loop going on here. And when downlink, uplink, and then it goes back. Of course, when there's downlink, the information goes to the cell phone. When there's uplink, the uplink has to go all the way back to the initial caller, which is like a person here who is trying to call. So let's look again. The cell phone is giving data out for the uplink, and the uplink transmits the data back, and it goes all the way back to PSTN, and the PSTN gets it back to the original caller. That's what happens in terms of architecture. And in terms of the protocol, in terms of the message exchange. So yeah, that that's about what's going on here. Then the protocol architecture is you have a mobile station. You have a mobile station. Let's look at the terminology here. You have base station, BSS mobile application part, and BTS management, and you have connection management, and you have link access protocol, and also you have mobility management, you have message transfer part, and each of them is defined specifically in the protocol. And you have radio resource management, you have signal connection control point. So mobile station and base transceiver station, base station controller, and mobile service switching center. So each link CM connects with CM, MM connects with MM, and then they have to connect by the same protocol. Therefore, they have the same specific definitions. So you see link between switching center, controller, base station, and mobile station, and each protocol stack connects with their corresponding protocol stack here and also here. And functions provided by protocols. Protocols above the link layer of the GSM signaling protocol architecture provide specific functions such as radio resource management, controls setup, termination, and handoff of radio channels. So that's radio resource management. And then mobility management. You have this location and security. And then connection management connects end users. And you have mobile application part. It operates between home location register and visitor location register. The reason being that if a person, let's say a device is moving from cell to cell, there needs to be some sort of connection between home register and visitor register to say that this device is home or this device is at the visitor location. It has to be have a certain level of registration. So that mobile application part kind of doing the job to communicate between the databases. And there will be a BTS management base system. Then there is the CDMA cellular. IS-95 is the best known example of CDMA. Then advantages of CDMA for cellular. It has frequency diversity because it occupies all frequency bands. In the time and frequency domain, it occupies all frequencies and all times, except the users are identified divided by code. That's what we mean by this C code. Uh, code division multiple access. So the frequency dependent transmission impairment has less effect on signal. So for example, if a certain frequency is shadowed or it's put in the degradation region, then because CDMA has frequency diversity, so it's jeopardized, but not as much as FB. It's not jeopardized as much as frequency division. So it has less effect. It still has effect, but it has less effect. And then multipath resistance. The chipping codes used for CDMA exhibit low cross correlation and low autocorrelation. And also the privacy. Privacy is inherent since spectrum is obtained by use of noise-like signals. So the privacy is inherent since spectrum is obtained by use of noise-like signals, meaning that the CDMA code division, it has a code. In fact, not a single code, but multiple codes. The code is noise like pseudo random sequence. So it works like noise. As a result, if you don't know the code, if let's say a third party person, he's trying to eavesdropping the signal, he does not know the code, he cannot eavesdrop, he cannot cheat because he doesn't know the code. But because the code, is well coordinated in the system, so of course the authentic user knows it, but a third party unknown person will not be able to know it. So it works like noise. And also graceful degradation. The system only gradually degrades as more users access the system. Meaning that if you have more users, those users brings in noise, brings in interference, and they will degrade gradually. Instead of like a sharp degradation, it will just bit by bit gradually degrades. And the drawback of CDMA self-jamming, the arriving transmissions from multiple users, not aligned on chip boundaries, unless users are perfectly synchronized. So, meaning that the code is consisting of multiple chips. The chip boundary has to be well aligned. Then of course, in the real world, nothing is perfect. So there will be some deviation among the chip boundaries. And when the boundaries are not perfectly synchronized, then those codes are not synchronized. As a result, when they do the demodulation, some noise and interferences will come in, and there will be some interference or jamming coming in. And the other thing is a near-far problem. Signals closer to the receiver are received with less attenuation than signals far away. So sometimes some signals are stronger, some signals are weaker because of the distance. And soft handoff requires that mobile acquires the new cell before it relinquishes the old. So let's say you are moving at the boundary of your cell, then you need to acquire a new cell before it relinquishes the original one. And this is more complex than the hard handoff used in FD or TD schemes. Then types of channels supported by forwarding. Pilot. Pilot allows the mobile unit to acquire timing information. This is very important because, as you know, when people communicate, they sort of need timing information. Imagine that when the cell phone is communicating with the base station, what it does is it has to transmit signal. Then, of course, the signal has to be synchronized, right? Otherwise, when your signal is transmitted, the receiver doesn't know it's your signal. They will think of it as a noise, and therefore they have to get synchronized. Uh, then the thing to do is they need to acquire timing information and provides phase reference and provides means for signal strength comparison. So for example, you have to tune your power so as not to jam your receiver. You should not jam your receiver, right? You need to control your power at a certain level so that signal is received properly. So that's what pilot is doing. Then the synchronization used by mobile station to obtain identification information about cellular system. So it has to be used by mobile station to get synchronized. And paging channels 1 to 7 contain messages for one or more mobile stations. And traffic channel 8 to 31, 33 to 63. The forward channel supports 55 traffic channels. So what that means is uh, you have a traffic, you have a traffic. That traffic, all those things, pilot, synchronization, paging, their job is to help, to facilitate, but they are not real data. The real data is so-called traffic. Real data is, for example, voice, your voice, of course, complex in a certain way. That is your real data. Voice data or whatever data you have, but voice is a typical type of data. And that goes through channel 8 to 31, channel 33 to 63. And that's the forward channel. Forward channel suppose 55 traffic channels. Then forward traffic channel processing step, as I said, voice, speech, that's a typical type. So it's encoded at a rate of 8550 bps. Then additional bits added for error detection. So as a result, it will be more than this because you are adding extra bits for error detection. And data transmitted in 2 millisecond blocks with forward error correction provided by a conventional encoder. So the data transmitted in 2 millisecond blocks with forward error correction code. And then data interleaved in blocks to reduce effects of errors. So let's say you put this bit there and that bit here, you try to interleave the blocks. And data bits are scrambled, serving as a privacy mask. The way they scramble it is, like you put some bits interleave, that's also one kind of scramble. And scramble requires a mapping, right? For example, you put your first bit at the third location, you put your third bit at the fifth location, you try to scramble it. And the way they map it is in secret. So it's sort of like a privacy, because if the third party is try to steal the information, he cannot do it because he doesn't know the mapping. So that's the way to do privacy. And then power control information inserted into traffic channel. And also direct sequence. Direct sequence meaning the code division. So that's a direct sequence SS function. Let's place 19.2 kbps to a rate of 1.2 mbps using one row of 6 by 64 wash matrix. The digital bit stream modulated onto the carrier using QPSK modulation scheme. So this sort of explains the whole process for speech, how speech is encoded, error correction code encoded, the interleave scrambled, and then put into a direct sequence, which is also called code division. And then it maps into a QPSK and then gets transmitted. So the whole process is done. Okay, I think that this is the end of the third hour. The end of the third hour. So we will just take a break for a couple minutes, then we will come back.